Hey, hello and welcome everyone. Good morning, dear participants. Welcome to Ivus conference today, organized by Kaunas University of Technology. And my name is Professor Audrius Lopata. I am a chair of this conference, and I think that with each of you, we had kind of email-based conversation or something. So we organized the conference together with Vilnius University, Vytautas Magnus University, and this year to organizing committee joined University of Salamanca. And it is an honor to welcome you to this 28th International Conference on Information Society and University Studies, Ivus 2023. And the Ivus is an opportunity for researchers and practitioners to exchange ideas about past, present, and future trends in information society and university studies. There were accepted more than 30 papers for publication. A double-blind paper evaluation method was adopted to evaluate each submission, and selected papers will appear in conference proceedings. And we thanks a lot for co-organizers, universities, and wish you a very nice event. I also want to thank everyone who helped organize this event, including the heads of university administration, heads of faculty informatics, the members of the program committee, chairs of section, especially technical staff, and all others who contributed to conference, but I did not mention. And of course, the participants themselves, scientists and researchers, authors of articles and presentations. So today we will have the following sessions. So special session on innovation in IT, special session on artificial intelligence and cybersecurity, a special session on intelligent system and e-learning solutions. So we will start the session on innovation in information technology, and please follow the time scale and the rules. So it means that it will be great that you'll spend up to 8 minutes for presentation, and we'll have 5 additional minutes for questions and answer section. So we'll have in total about 12 or 13 minutes. Okay, so I would like to invite the first presenter, Rūta Buckiūnaitė. Together with co-authors Tadas Turskis, Marius Teleiša, and Dalia Čelnerytė. Okay, the floor is yours.
Good morning. I'm Rūta. This is Marius and Tadas. And we will present our research project, our study, which is mixed type data augmentations for environmental sound classifications. So as the name suggests, our study deals with environmental sound classification, and our goal for the study was to see whether our proposed mixed type data augmentations had any impact on the overall performance compared to results with no augmentations. I'll briefly present what we used. So the data sets that we chose were ESC15 and Urban Sound 8K. Both are relatively small data sets with 2,000 and almost 9,000 sound recordings of various environmental sounds. Because of that, we took some pre-processing steps. We used mellow frequency substral coefficients. For feature extractions, MFCCs are common feature representations used in the field of environmental sound classification because they capture relevant information about the spectral characteristics of the sound, while ignoring other less relevant characteristics, which makes them useful in a wide range of applications. MFCC is also relatively sensitive to various sound changes, like changes in volume and pitch, and they are quite low dimensional, so they help the computation process move faster.
So our proposed method is mixed type data augmentation. Usually this was at first used on image pre-processing. It works by mixing up two different data samples by using a coefficient. So let's say we use 60% coefficient. So the first image will be used as 60% strength, and the second image will be used as 40%. And the same is applied to the labels. In our implementation, we're using this on data of the same label, so as not to mix the labels. And this is not a novel approach, but this is usually applied to image pre-processing. And as we are representing the audio signal as an image, we can apply it also to audio signals. And we can see here some of the methods that we used in our approach. Our proposed methodology is first the feature extraction using null frequency spectral coefficients, then doing an online data augmentation, and then using that directly in the model to have an output. The testing was performed, as mentioned, on ESC50 and Urban Sound 8K datasets using a 75-25 train test split. Then we used mix-up coefficients of 0.2 to 0.3 and so on. And we also have an augmentation probability that determines how often a sample will be augmented.
Okay, so we did 5 testing for each data set, and we analyzed the results from 3 different angles. So first one is using a probability of different percentage. So as we see in this results table, we once we used 50% probability, we had most best results in most cases, with some exceptions to 30%, and in one case to no augmentation, but it was quite a very low difference. So the next angle was using mix-up coefficients percentage. So here we see that results are a bit scattered, but mainly from 70 to 80% mix-up coefficient gave the best results for ESC50 dataset. And here just want to note that probability of 100% was excluded from the results in this table. And then the last angle was just looking in the results of all different methods. So we see that for this ESC50 dataset, mix-up gave the best results in most categories. Just some of the others were slightly better in different methods. And same we did for US 8K dataset. First we looked through the probability angle. So here we see a bit different results that using, like before, using 50% gave also good results, but here as well no augmentation also showed practically same or even better in some cases results. Here we did also the same. We excluded 100% probability augmentation from further results analyzation. And here we see usage of 20 to 30% mix-up gave best results, and also here we see that no augmentation on average also gave better accuracy, while 20 or 30% gave better loss. And here, once looking through different methods, we see that random columns mix-up gave better results in most cases, and some other methods had just the same exact results in few categories, but the best one was random columns mix-up. So as to discuss, we see that column mix-up performs better than the row, so which suggests that this kind of information is getting from image signal, that it goes horizontally. And for experimental testing coefficients, usage of 20 to 30% or 70 to 80%, we might argue that it could be the same set of images, but however, a set of training epoch is when training epoch is finite, and 70 to 80% mix-up coefficient guarantees that the augmented set will always have one of each sample as the dominant image, and 20 to 30% is reverse. And then when comparing ESC50 and Urban Sound 8K datasets, we saw that there were more improvements for the first one, but it could be due to that it had only 40 examples per class, while US 8K has up to 1,000 images per class. So for future research, it could be useful to look into datasets that has even fewer results, because usually augmentation helps here most. And as a conclusion, we saw that ESC50 dataset mix-up augmentation gave better, highest accuracy and lowest loss compared to no augmentation. For Urban Sound 8K dataset, we saw random columns mix-up gave the lowest loss, but identical accuracy to augmentation. But here, as we discussed, it was due to that Urban Sound 8K has quite a lot of images per class. Then also we saw that usage of probability of 50% or 30% gave the best results, and probability of 100% gave even worse results than using no augmentation. And yeah, that's basically it. Thank you.
Okay, thank you. Do we have questions from on-site participants? Okay.
Maybe one. So you have used those augmentations to check how does the computer recognize it. Did you try the same with, well, neural network? How would you recognize those augmented sounds?
No, this approach was, as I mentioned, first used in images, and this is not a very, let's say, logical way to combine images. And let's say you have a cat and a mouse combined into one image. Your brain cannot process what this is, but a neural network is not completely the same as our brain, so this is an interesting approach, and which is why we tried to test it.
Thank you. And I would like to ask one question. And what about the practical implementation of your methodology? Do you have kind of ideas how to put it into the practice, or do you have kind of plans or something?
There were no plans to implement it
Personally,
yeah, but of course it's always useful to implement augmentation, and for such cases, yeah, as we mentioned in discussion, it could be useful once we need to enlarge a very small data set. So this would be practical usage, I think, for such scenarios.
Okay, thank you. More questions? Okay, thank you. And now I would like to invite the next presenters. We'll have the we should have the presentation named click prediction using unsupervised learning methods. And the authors are Vitalijus Rapinaitė, Ignas Splinskas ir Ingrida Lazdynytė Budnė.
So good morning, I'm Vitalia, and today I'm going to present you our paper, Click Prediction Using Unsupervised Learning Methods. So the third-party cookies is an effective tool for digital marketing. However, the cookies will be removed from Chrome by 2024, and it's already removed from other browsers. This creates a need for effective yet non-privacy intrusive ways for recommendations of ads. So maybe it's time to look at the context. Here we can see example of an article which contains information about the garden trends. And we can also see an ad that consists an image of a game which and the text suggests us to play the game to escape the reality. However, if we change the banner into more text-related banners such as plant recommendation, then we could get more clicks from the users since it's related to the context. And this kind of marketing is called contextual marketing. However, there are some issues and limitations. Click-through rate varies between 0.1 and 4%. There's class imbalance between views of banners such as impressions and clicks. It's also a difficult problem to solve since there's lots of data. And we also had some limitations in our research, such as limited resources, and we did not get access to the banner image data. So the solution was to use simple yet effective algorithms that are proven to work. So the unsupervised learning algorithms were used for the click prediction. Contextual data was used to train the models, and the models learned what is normal behavior of events that result in clicks. Models could recognize ad views as outliers. So as we can see on the right image, the outliers would be impressions or views, and the green points would be the clicks. So here is a short description of the mobile app data, which was used to train our models on clicks. There were three types of data, such as information about the banners, descriptions, landing URLs about it, and mobile app descriptions, mobile app categories, and some information about the users, such as region, event metadata. In total, there were 19 features, but more features were generated. So here is the data processing steps which we use in the paper. So the generic processing consists of filtering out mobile app IDs with low occurrence rate and then values removal and replacement. Categorical data was converted into integers, and textual data was processed using the pipeline seen on the right side, such as normalizing text, removing punctuations, numbers, and redundant characters, also removing stop words using an LTK library. Stop words are words that do not contain useful information for the models. And after that, the text was lemmatized, creating the easiest form of the word, and glove representations were extracted from the lemmatized words. So the algorithms selected for the model training were local outlier factor algorithm, which is novelty detection algorithm, and it is k-nearest neighbor based algorithm. And another algorithm was isolation forest algorithm, which was tree-based algorithm used to isolate data points. Data points that can be easily isolated are outliers. So the training sets. The models were trained on click data, and additional features were generated from weekday and daytime word attributes, such as Friday or evening, and glove representations were extracted from them, creating second version of dataset. So 5 experiments were performed on different dataset variations. The original dataset, which consisted of data after processing steps, the original data with 50 and 25 principal component analysis components, and the second version of data with 50 and 25 principal component analysis components. So here we can see our experiment results, and isolation forest performed the best compared to local outlier factor algorithm when PCA of 50 was used on the first version of dataset. The second best result was received with the same algorithm when they were used 50 components on the second version. The local outlier factor algorithm performed worse in most cases. However, it started performing better when we added additional features. So the final results are the isolation forest algorithm was selected as the best model, trained on the first dataset with 50 PCA components. The test data consisted of 10,000 samples, 5,000 impressions, and 5,000 clicks. And as we can see from the image on the right side, the model performs worse than the dummy classifier since it reaches 42.7% accuracy, and the dummy classifier can achieve 50% accuracy when it predicts a single class. So historical data is required to make better predictions, and context is not enough. So that's all.
Thank you. Do we have questions from the side? Okay, I have one.
Okay.
I am, let's say, regular user of kind of mobile applications,
Yes.
IT technologies, and so on. So, how your method should be useful for me?
It would give better recommendations for you as a user, therefore it would increase your satisfaction with the app.
Okay. What kind of app? I should install kind of plugin or?
No, it would be integrated in the app,
Okay.
same as it's already used.
Okay.
Yeah.
Okay, it's clear. More questions? Okay, I'll check. Do we have maybe questions from remote users? No? Okay, thank you. Thank you very much. And next presentation. It's named Reinforcement Learning for Obstacle Avoidance Application in Unity ML Agents. And the presenter will be Mahmoud. Okay, hello. The floor is yours.
Yes. Good morning, everyone. This paper is one part of my research project. With our title is related to the reinforcement learning for obstacle avoidance application in Unity and agents. Honestly, when I started to work in this project for myself, it was really exciting or amazing, to be honest. Our goal in this paper is comparing two methods for avoidance obstacle with Unity, how to say that, in a reinforcement learning in Unity environment. And objectives part, it was working, added some obstacle in our environment. And after that, for example, using best model in how to that our algorithm, it calls PPO. And the second part is the train part agents, our agents with two demonstration for obstacle avoidance. And today most of the people using Unity environment with different machine learning like PPO, SHD, or I don't know, Polka algorithms, because as allowed to a developer to use, so how to say that, with the machine learning, different machine learning in a simulation to the Unity. And another part, so I want to talk about ML agents, machine learning. We have some machine learning algorithm like PPO, RNN, SHC, TD3, or Polka. So the best model here, I use it for our agent. It was the PPO. So, and the second part, another part is we have a two demonstration for our behavior tab, like behavior cloning. And again, that part for also myself, it was a question. So, okay, what's the difference between behavior cloning and the game? So, behavior cloning try to copy expert or copy of the, how to say that, recording and human behavior, but Gil try to understand expert. So that part is a Gil is a gets difficult to resolve with comparing with the behavior cloning. So our environment, we use it. This part related to the Unity AI racing car simulations, and so this environments, as I said before, is in a Unity part, Unity software. Here we have a 24 card agents, you can see, and they have a two sensor to understand any checkpoints and any obstacle to avoid this. So here I improved our environment. I added some obstacles in our environment to train our engine and to avoid them. So another part here, we have our result comparing between behavior cloning and GEL. This chart related to the reward value, and so for I put it a 5 million step to train any agent to house the behavior. So we can see the behavior cloning, we get better than result comparing with the gate part. Here is the result of the loss value, and we can see the loss value also related to the behavior cloning. It was better than Gale, and that was, and also we get a result with the TensorBoard and the online how to say that the time series with the Unity in our results. And here, yeah, you can see with the behavior cloning, agents try to train abundance our obstacles. Yeah. Okay. In conclusion part here, we can say that so we use that simulation. We will train our agents with the reinforcement learning, and we use a two demonstration. One of them was behavior cloning, and one part was a game, and one of another things is various reinforcement learning algorithms you can set up and using for training in any agents in Unity machine in a Unity environment. And the behavior cloning, the loss value, it was 0.019, and reward part is minus 1.6, and the yield part you can see is minus 2.092 in the reward value, and in the loss value it was 0.09. And so the Gale model didn't perform well, it's not good evaluation. So behavior cloning, it was successful for my result. Thank you so much.
Okay, thank you. Do we have questions from outside participants? Okay, we have one question.
Sorry for this, but was the training done on only one map, or and if it's only on one map, will the agent be able to?
Yes, I have one environment, honestly, but I try to put it random obstacles to for I don't know, maybe 4 or 5 times. Okay, just behavior cloning was a success result. For any random obstacle, you can train your agency.
Okay, and I have one question. You mentioned that all your experiments were done using Unity platform.
Yes,
right?
Unity
And
platform.
what about the different kinds of
In
platforms?
other platform, you can use the mattress. We have a two simulation. When I check it, one of them it was mattress, one of them it was Unity. But I use the Unity because is how to allow us to use reinforcement learning algorithm is better than with mattress. That's why I use Unity.
Okay,
Yes.
okay, thank you. More questions? Okay, thank you very much. Okay, and now we'll have next presenter. Presentation fast approximate pathfinding based on 2D convolution. Presenters be Marius, Elisha, and Kolko Dalia Čilnerytė. Okay.
Hello, my name is Marius Tereisha. I study in Kaunas University of Technology, and today I'll be presenting my paper on a new pathfinding algorithm. My professor is Dalia Čilnerytė. So pathfinding is a classic problem of finding a path of shortest cost between two given points, where cost is most likely the travel distance. This paper focuses on uniform cost grids, which are a discretization of the environment, and they can be often utilized in video games. A popular way of representing a grid can be seen in this figure, where white tiles are traversable nodes and black tiles are obstacles. The problem of grids is that it is one of the more inefficient representations for pathfinding, as it can require significantly more memory and computational power to perform pathfinding due to the large node count. These resources are often short in supply in video games, as for example, various logic, including pathfinding, must complete within 16 milliseconds so as to maintain a smooth user experience. Grids can also have a different connection logic, such as 4-way, where the algorithm can traverse in cardinal directions, and 8-way, where all the 8 neighbors are available for traversal. More neighbors also means more edges, which results in increased search time. Then there's also the question of rules about diagonal traversal near obstacles. So for this work, we decided to reduce the scope and go with 4-way connection, but 8-way adaptation can and is being implemented. So a core problem of uniform cost grids is path symmetry, which means that for almost any pair of nodes, there exist multiple equally optimal paths. This figure shows only 3 of them, but there are a lot more, and the count only increases with greater distance. A pathfinding algorithm, such as A-star, must evaluate many of these redundant paths, which can slow down the search significantly. There's even a pathfinding algorithm dedicated to breaking path symmetries, which is jump point search, and has shown to be an order of magnitude faster, but it was not utilized in this work, so I'll not delve into more detail. Back to A-star, which is a classical pathfinding algorithm and is often used for pathfinding in grids. A-star is optimal with an asterisk and complete, meaning that it will always find a path if there is one. A star utilizes heuristic functions, which guide the search towards the goal to reduce search time. And this is where the asterisk stems from, as heuristics will also determine if A star will find an optimal path and how many nodes will be explored. Classical heuristics are also static, meaning that they provide an optimistic estimate that does not consider obstacles and will not change over time. Different grids can require different heuristics. For example, on a four-way grid, meaning that the grid can only be traversed in cardinal directions, the Manhattan distance is suitable. However, that same function will overestimate paths on an 8-way grid. If our heuristic does not return true optimistic distance on a specific grid, the pathfinding algorithm will either find a suboptimal path or expand more nodes than it needs to, which will slow down the search. In this work, we've elected to use Manhattan, Euclidean, and squared Euclidean distance heuristics. Even with the help of these static heuristics, the L-star algorithm may not be fast enough for larger grids, so there's a need for a faster alternative. Hierarchical pathfinding A-star or HPA-star is a hierarchical pathfinding algorithm which creates layers of compressed map representations on which a search can be performed faster. In the offline preprocessing stage, this algorithm partitions the map into larger squares, designates entrances and their entry points, which are marked green. And during an online search, the abstraction layer is formed from those entry points, and the path is found first in the abstraction layer and then in the real grid. Grids can also be represented as a 2-raster image, and a popular image processing technique is filtering, such as Gaussian blur. Filtering is generally performed as a series of convolutions using sliding window principle. This technique can also be used for feature extraction, which gave us the idea to use it for pathfinding. So the proposed algorithm in this paper combines both 2D image convolution and hierarchical pathfinding, which results in convolutional hierarchical pathfinding A-star algorithm, or CHP A-star. During preprocessing, the map is partitioned into square segments by using a sliding window. For each segment, a search is performed to find any valid path which crosses into the neighboring segment to the right or below. The segments are then used as nodes in the abstraction layer and are connected to the corresponding search of the segment finds a valid path. During an online search, the start and goal paths are translated into the abstraction layer. A search is performed inside the abstraction layer using A-star. The nodes of the resulting path are translated into the real grid and then used as checkpoints for A-star for the final search in the real grid. Translating from the abstraction layer to a real grid may not be optimal. So to increase optimality, a p-step parameter is introduced, which defines the step for taking the checkpoints. So for example, with p-step 1, the algorithm will use every checkpoint, and for p-step 2, it would use every second checkpoint. The experimental setup was performed on pathfinding benchmarks from video game StarCraft. All algorithms were implemented during this work, so CHP star will be using the same A-star implementation as A-star on its own, so there will not be any differences in optimization. The programming language of choice was Python, and the algorithm search times were rather long, so benchmarks had to be reduced. So each map has a scenario. The paths are sorted by path length, so for testing we divided it into the 200 segments, and one randomly drawn path was picked from each segment. So first we have a p-step analysis. As we can see, p-step reduces path length non-linearly, where jump from p-step 1 to p-step 2 results in 8% path length reduction, and improvement declines rapidly afterwards. As p-step is increased, so does the explored node count. However, there seems to be somewhat of an anomaly with the p-step 2, but this might be due to low test count. Unlike p-step 3 and p-step 4, the anomaly. In any case, p-step 2 has shown the best balance of path optimality and exploration, so it will be used in the further experiments. Next, we have analyzed the effect of heuristic functions on path length and exploration. Euclidean and Manhattan heuristics achieved the expected shortest path, However, we can see that the Euclidean distance explored 50% more nodes because it overestimates the true path. Squared Euclidean distance explored less than a quarter of nodes when compared to Manhattan distance, but at the cost of 19% longer paths. Shifting focus to CHPA star, the heuristics have very little effect on path length, where the optimal Manhattan distance and Euclidean distance heuristics can even result in longer paths. The heuristics do affect node exploration, where the Euclidean distance is as expected, resulting in the most explored nodes at 18,000. Surprisingly, both phase Manhattan distance configuration resulted in the least explored nodes, which is 6% less than the second lowest configuration. Both phase Manhattan distance configuration on average found 14% shorter paths and explored 20% less nodes than A star with the squared Euclidean distance heuristic. So it is a better alternative, albeit more complex to implement. And finally, we have search time average, where CHPA star on average finds paths 97% faster than A star with the Manhattan distance heuristic and P-step 2. Since CHPA star utilizes A star, the complexity will remain similar to H star, which should be log of n. And finally, the problems of this algorithm: it is incomplete, as there can be preprocessing artifacts which lose some information. So we have in longer paths where the algorithm sees a path where it should not exist. But in the second iteration of the algorithm, we are trying to improve this. Question?
Okay, thank you. Do we have questions from on-site participants? Okay, we have one question.
So, well, you tried it with, grid like chessbox. Would things be significantly different if you would try a different grid, like, for example, made of hexagons, that is like in some basic strategy games which use those? Would something be easier, better? Would it be possible to adapt this method there?
I'm not sure. This algorithm is specifically targeted towards the square grid, so I'm not sure. I highly doubt that it would be adapted to a hexagon grid, but the hexagon grid has almost the same problems of path symmetries, and it is a not efficient way of representing a graph. So a better way would be using the navigation mesh, where it uses the checkpoints on each obstacle to reduce the no count.
Okay, I have one question. So, in general, what about the future works? What are the next steps of your study?
Currently in Masters, I'm adapting the algorithm to 8-way pathfinding and trying to reduce the artifacts of preprocessing, but there can be more done as for example, the checkpoint order does not have to be in sequence. We can find the paths in parallel. That should reduce some time. And also, I'm only using one abstraction layer. There could be more abstraction layers used, and really research can be done on that.
So you have a lot of things to do, yeah?
Yes.
Okay, so thank you very much. Okay. And next our presentation is named recursive weighted two-mean split algorithm on the segmentation reduction. And presenter will be Cornelia Magilaitė and co-authors Lukas Arlauskas and Karolis Pisek.
So, hello everyone, my name is Cornelia Magilaitė, and I am here to present my team's work called Recursive Weighted Two-Mean Split Algorithm for Under-Segmentation Reduction. So, machine learning models rely heavily on depth data for processing. While depth sensing devices can provide this data, manual segmentation is a repetitive task that requires a lot of manual labor. Trying to use up this problem, there has been a research in trying to make this process as automated as possible. The experiment was made using K-means algorithm and random forest classifier. However, the algorithm exhibited poor efficiency when presented with complex and combined datasets, as it failed to accurately trim the edges of the image. As such, the goal of this research is to enhance the accuracy of the current solution in recognizing complex poses, while ensuring that the accuracy in recognizing simple poses does not decline. So random forest is a supervised machine learning technique that contains of multiple decision trees that vote on the final decision. It can be utilized for segmentation tasks. However, in this case, training requires the use of features. These features can be handcrafted or computed by machine learning systems. In the state of art, handcrafted features are wildly various. However, they are always different and depend on the specific tasks. K-means algorithm is an unsupervised learning technique used for clustering. The original algorithm treats all centroids with equal weights. There are many variations of the algorithm that try to introduce different weights for the clusters. However, there are several challenges when applying weighted K-means algorithm. In the state of art, it is solved very differently. For instance, it could be pre-selecting different features, estimating variable relative relevance. Some weights may be acquired using machine learning. Unfortunately, there is no best single way to solve this problem. So the primary objective is to enhance the accuracy of the segmentation process. Implementing the one-to-one cut methodology currently achieves 55% of accuracy for complex data sets. However, further enhancements are necessary. It currently struggles with trimming smaller edges of the image. In the worst-case scenarios, the whole scene is treated as one segment with human occupying around 10% of the pixels. And using one-to-one ratio, the first cut retains 50% of the scene, the second one 25%, and the third cut requires fitting the entire human element into one cluster. And in those cases where only the edges need to be trimmed, there is no way that one-to-one sensitivity can achieve this. So the aim of assigning different weights to the centroids is to improve the process of partitioning the data points. Decreasing one centroid's weight makes the other centroid more sensitive, and consequently more data points will be assigned to the centroid with lower weights. In cases where only the edges need to be trimmed, using different sensitivity ratios can improve the results. The main challenge is to determine the most optimal sensitivity, as well as decide which centroid should be more sensitive. To determine the required ratio of sensitivities, the proportion of weight had to be identified. The ratio of weights was chosen from the range of 0 to 1 with a step of 0.1. To decrease the sensitivity of a centroid, a lower weight was assigned to it. This indicates that the multiplication between calculated distance and the fixed weight resulted in a lower distance for the second for the centroid that has lower weight. As a result, it's a higher possibility that the point will be assigned to that centroid. However, the weights ratio may differ, and to identify the most optimal accuracy, an experiment was performed. So the whole experiment process contained of 4 steps. Initially, the desired weights were set to determine the centroid sensitivities. The goal was to test all possible combinations that identify the most optimal solution. Subsequently, data was generated for the classifier. The data used for generation consists of depth images of people, and this data was acquired using Kinect sensor. After the generation, a dataset was created that will be utilized to train and evaluate the performance of random forest classifier algorithm. And finally, the segmentation accuracy was assessed by obtaining mean accuracies for simple, complex, and combined datasets. So the results contain mean segmentation accuracy. For the hypothesis to be confirmed, it was important that the accuracy for the simple data set would not worsen and would improve over the baseline with complex and combined data sets. The superior results were obtained when assigning lower weight to the second centroid. The best results for simple dataset were achieved with second centroid weight of 0.5, while the best accuracy for the complex and combined datasets were obtained with the second centroid weight of 0.4. The best accuracy results are marked in yellow. Interestingly, more than half of the results obtained with a simple dataset were rather close to the best solution. The weights are from 0.1 to 0.4. When comparing the results of random forest classification with different second centroid weights, the best precision, recall, and F1 score for the correct cuts were 0.96, 0.97, and 0.96 respectively, while the best result using the same metrics for incorrect cuts were 0.98, 0.97, and 0.98 respectively. The best accuracy achieved was 0.97, so the best variant was the one with the second centroid weight of 0.4. The presented images demonstrate several mistakes made by proposed algorithm. In all cases, the undersegmented area is placed around the human. The last 3 examples shows that the cluster weight should be very different to cut such small pieces on either side of a human body. Unfortunately, this is limited by the classifier accuracy. Despite that, the manual work required to remove the red areas of the images is lower than presented in the original research. The second image shows an error that occurs due to centroid positioning. The algorithm decided that cutting legs of a human would add more accuracy instead of leaving too many pixels in the output, which leads to a different but smaller mistake. So in the performed experiments, several weighted k-means variants consistently outperformed the baseline unweighted one. Using 0.5 as second centroid weight achieved accuracy of 82.94% for a simple dataset, and the complex and combined datasets benefited the most from 0.4 as second centroid weight. The classification reports revealed that the variant of 0.4 achieved the best results for all metrics. Our research findings indicate that the use of weighted k-means algorithm is more suitable for human body segmentation. The further research that could be done is further optimization of the algorithm for the complex and combined datasets with the aim of improving the accuracy of segmentation. Thank you for attention. If you have any questions.
No questions? Okay, I would like to ask, so you mentioned about the accuracy 82.94%, yeah? So is it, top level accuracy, or it is possible to go on and maximize?
Well, currently this is the maximum accuracy for simple data set, but in the future it will be interesting to use different techniques to improve this algorithm. It could
For example, what kind of techniques?
One of the techniques, again, to test with more coefficients, maybe choose coefficients from different ranges. Of course, well, maybe choose, instead of 2 centroids, make 3 or 4, because now the algorithm is called 2 means. That means that the cluster is split in 2 parts. And the experiment can be made with splitting the cluster into 3 parts or 4 parts. So this is up to experimenting.
Okay, 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 thank you. And okay, now we will have two recorded presentations. So I will try to start.
Hello, my name is Anita, and today I will talk about influence of aerial image resolution on detail detection accuracy. So object detection involves finding the numerous objects in the images and identifying their location. Recently, object detection has been considered one of the most challenging tasks in computer vision. So it should be noted that the engineering application of detail detection from aerial images is a difficult task due to particularity of perspective, the small size of the object, and the complex background. So the goal of this study is to investigate the change in the accuracy of object detection models for detecting details in aerial images when the resolution of the images fed to the models is reduced. The findings of this study might be useful when certain situations require quick and real-time decision-making regarding the distribution of details in a geographic space if collecting aerial photographs of this space is available. When it is known what minimum resolution of object detection models are sufficient to obtain acceptable results from aerial image, it is possible to save time for flying drones, such as unmanned aerial vehicles. Also processing information and presenting results. So in this slide, I would like to mention the method of this study. So deep learning algorithms have allowed detailed identification technologies to attain very high performance. The deep convolution neural network may use the data set to train and enhance its model independently. Deep learning-based object detection algorithms are classified into 2 categories, one-stage detectors and two-stage detectors. In this work, we decided to use one-stage object detection algorithms such as YOLA. YOLA means you only look once. This algorithm doesn't require to use the region proposal network to extract candidate target information. Moreover, it directly generates the location and category information of target through network, which is end-to-end target detection algorithm. Therefore, the single-step target detection algorithms have a faster detection speed. The model selected for this study one of the best performing one-stage detectors, as you see, YOLA version 5, 6, and version 8. That research that reach high accuracy and speed when applied to object detection tasks. Also, in this work, we use 2 data sets. The first one is vehicle detection in aerial imagery dataset, that it's VADI, and that addresses the task of small vehicles detection. The vehicle detection in aerial imagery weather database includes various diagrams such as woods, cities, roads, parking lots, construction sites, or fields. In addition, the vehicles to be detected have different orientation and can be altered by specular spots or masked. Each image is available in several spectral bands and resolutions. Also, the data set has 9 different classes of vehicles, such as plane, boat, camping car, van, truck, and others. Also, there was 2 meta classes, such as small land vehicles and large land vehicles. The small land vehicles class consists of classes car, pickup, tractor, and van, and the large land vehicles class contains the truck and camping car. When preparing the radar data set for the experiment, these classes have been dropped. Plane, boat, camping car, tractor, truck, and other. Well, these changes were done in order to have comparable visual data about the vehicle. So only one class car was left in this data set. Also, we use one more data set. It's COX. It means the car's overhead with context. And it contains many unique cars. It's more than 32,000. And also it includes 6 different image sets, each covering a different location and produced by different images. And let's go to the another slide. So probably the most important step is data processing. So during data pre-processing, only one class car was selected from weather and COX data set. Also, negative samples class from the COX dataset was dropped, and from weather dataset we removed planes, boats, camper vans, tractors, and trucks. And also, it should be noted that RoboFlow platform was used to manage the dataset. For each evolution sample, the dataset images were proportionally reduced in size to achieve the desired centimeters per pixel ratio. Also, figure 5 demonstrates that the weather dataset has mostly from 2 to 4 vehicles per image, and the figure 6 depicts COX dataset that has mostly from 2 to 49 vehicles per image. So evolution metrics. So in this study we use total detection speed in milliseconds, precision, recall, mean average precision, also confusion matrix. Precision, the metric precision reflects the model's ability to distinguish negative samples. The higher the precision, the stronger the model's ability to distinguish negative samples. Recall reflects the model's ability to identify positive samples. The higher value of the recall, the stronger the model's ability to detect positive samples. The F1 score is a combination of recall and precision, and it might be obtained from equation 3. Also, other metrics that we use is mean average precision that might be obtained from equation 5. Also, intersection over union might be determined according to equation 4. As you see, there is a formal description in this slide, and also it might be found in our article. And during the experiment, the process is indicated by figure 7. So as you see, it is process called diagram of experiment. So the first step is to obtain the data set files at original resolution. Then we need to resize all images to the desired metric and split data into training, validation, and test sets. The third step is we need to provide the data set variation to the model as input training data. Then start custom training the model and using developer provided weights as the starting point. And the last one is to evaluate the newly trained model on unseen test data and capture the evaluation results. So, for the training of the models available pre-trained weights, we use it as the starting point for each variation of data set. Regarding the data set split, both data sets featured the same data split, 70% training, 20% validation, and 10% testing. So here is some of our results. So it was found that on the weather data set, precision, recall, and mean average precision indicators values are smaller than on the other data set. However, the testing speed was higher. When the data set had the lowest pixel ratio, which is 32.5 centimeters per pixel, the algorithm Java version 7 model obtained better test results on the COPS dataset than the Java version 5. However, Java version 5 demonstrated significantly higher values on the weather dataset than the Java version 7. For the COPS dataset, Java version 7 achieved mean average precision 1 minute. Java version achieved mean average precision score of 0.93, while Java version 5 achieved 0.88, and under the same condition. For the weather data set, algorithm YOLO version 7 achieved mean average precision score of 0.029, while YOLO version 5 achieved 0.248. Java version also should be noted that Java version 7 had a faster total detection speed across all data sets and the variation. As we see on the right, the figure 9 depicts the change of accuracy metrics of all models changes with the different data set when the image pixel ratio was reduced by 5 or 2.5 centimeters. So the main results are presented in the table last. And here is some conclusion. In this study, the change in the accuracy of detailed detection using reduced pixel ratio error image was investigated. It was found that one-stage object detection algorithm, YOLO version 5, YOLO version 7, and YOLO version 8 achieve an average of 3.51% lower mean average precision scores when the image pixel ratio is reduced every 5 centimeters per pixel. Also, the YOLO version 8 model had the most stable results among other models, decreasing by an average of 0.24% when tested of the cost data set from 12.5 to 27.5 per pixel image pixel ratio. While all models performed better on the COGS and not on the weather data set during testing, the weather data set only had 2,807 annotated vehicles, while the other data set was much larger. It's more than 32,000 annotated vehicles, which may have influenced the testing results. It should be noted that vehicles in the weather data set were labeled, even if some of them were partially hidden by other objects or just partially visible at the edge of the image. When the models were tested with the cost data set, results dropped by an average of 0.68% and by an average of 6.85% with the weather data set when used image pixel ratio between 12.5 and 27.5 centimeters per pixel. And the last conclusion, more pronounced changes in the mean average accuracy of the models are not noticeable when the pixel ratio varies from 30 to 32.5 centimeters per pixel. And when the pixel ratio was 30 centimeters per pixel, then accuracy decreased by an average of 1.42% on the cost data set, and talking about weather data set, it was 11.96%. When the pixel ratio was 32.5 centimeters per pixel, then accuracy decreased by an average of 3.23% on the cost data set and 72.84% on the weather data. And of course, we have questions and answers, and don't afraid and contact us. And here is corresponding author, Donata Globichuta. Thank you for your attention and have a nice interaction.
possibility to provide your questions by email directly to corresponding author. Okay, thank you. And now we'll have the final recorded presentation. It's named Epidemiological Model Based on Coronavirus Data. Yes. So I'll try to start with presentation, and it will be the last presentation in this section.
The link based on coronavirus data. The article presents selected compartmental epidemiological models. The SI model is discussed, which is considered to be the most basic epidemiological compartmental model. The SVIR model was also analyzed, which additionally takes into account, for example, use of vaccinations. In addition to theoretical elaboration, the article also includes simulations based on real coronavirus pandemic data in selected countries. The obtained results show that on the basis of real data from a certain period of time, it is possible to predict the trend of the further course of infection in a given population. The models analyzed in this article are also called group or compartmental models because a given population is divided into groups, subpopulations, due to the state of health, the possibility of infecting other individuals, or the level of resistance to a given disease. The first analyzed model is SI model. We analyze a closed population of n evenly distributed individuals. There are two separable subpopulations. A subpopulation of individuals susceptible to infection, denoted as S, and a subpopulation of infected individuals, denoted as I. Figure 1 presents a diagram illustrating the possibilities of individuals to move within groups in the analyzed population. Note that individuals can only move between this group in one direction. If an individual from subpopulation S gets sick, it automatically goes to the group of infected individuals, and it's no longer possible to return to subpopulation S. We can describe the considered model using the following system of differential equations, which is given by the formula 1. Next model is SVIR model, in which we also consider a closed population of n individuals. The analyzed group of evenly distributed individuals is divided into the following subgroups. The subpopulation of individuals susceptible to infection, denoted as S, a subpopulation of vaccinated individuals, denoted as V, a subpopulation of infected individuals, denoted as I, and a subpopulation of individuals who have already suffered from the disease, denoted as R. Figure 2 shows a diagram illustrating how individuals can move between subpopulations. It's easy to say that a susceptible individual can become vaccinated and thus end up in the V subpopulation. Another possibility is that the individual becomes ill as a result of contact with an infected person. In this case, the individual is transferred to subpopulation I, And then, after recovering from the disease, the individual is transferred to subpopulation R. The SBIR model can be represented by a system of differential equations given by a formula 2. The next part of our article are simulations, and we can start with a simulation about coronavirus pandemic in Bulgaria. We analyzed the time period from October 21, 2020 to January 19, 2021. We assume that the size of the population in which the epidemic broke out is equal to the total number of all confirmed cases of infection from the beginning of the outbreak to the last day of prediction, I mean the end of the considered infection period. In the SBIR model, N is also affected by the number of vaccinations performed to date. So in our case, N is approximately 230,000. First, we fit the model SI parameters to the initial 31 days using the last squares method. Then we did ex post prediction to see if the model with the determined parameter correctly reflects the trend of the disease development during the next 90 days. And as you can see, the average error of the predictions obtained from the model does not even exceed 1.5%, so it's small error. Next, we can see a simulation about coronavirus pandemic in Denmark. We analyzed the time period from February 26, 2021 to April 16, 2021. And we assume the population size as you can see on the slide. And first we fit the model SBIR parameters to the initial 20 days using the least squares method. And then we did ex post prediction. The data about infected population we get from the simulation differ about 15.85 to 18% from real data. We can see that when comparing the predicted data about received about recovered people with the real data, they differ by smaller, by less than 1%. So it's different between them is really small. In the case of vaccinated people, the simulation data differs by about 6.47 to 11.3% from real data. And according to the assumptions of the model, the average duration of illness per person is 1 over gamma, and it's equal to approximately 13 days. It turns out that this information is consistent with the facts reported in literature because the average duration of SARS-CoV-2 infections is considered to be 2 weeks. So 13 days is okay. Conclusion, It turns out that even the simple SI model can correctly reflect the actual trend of coronavirus development in selected countries. Moreover, this model can be modified relatively easy. Thanks to this, it's possible to include more factors influencing the development of disease in considerations. And the results obtained from the performed simulations reflects the real data with a certain error. It can be assumed that this is due to the fact that the model does not take into account all the factors that affect the development and spread of the disease. And that's all what we prepared. Thank you for your attention.
Thank you for presenter. Yeah. And it was our last presentation in this session. So I declare this session closed. So thank you very much for attention, and we will immediately switch the broadcast to a remote session moderated by my colleague Daina Gudonene. So it's up to you. Would you like to stay or would you like to leave? So, but thank you very much for participating on site right here in Kaunas University of Technology. And so I hope to see all of you next year. Yeah. Thank you very much. Thank you.